All right. Um, my name is Praveen Viraraghavan. I'm a technologist at Seagate, uh, working on data center architectures and our alignment into them. One of the slides I actually showed yesterday was, just where have we been and where are we going? And it's just been a decade by decade evolution of data demand related to hard drives, to the cloud, and now we're into this AI window. And as you've seen through all of the presentations over the last few days, the impact of AI to cooling, to networking, to power usage, and even physically lifting the rack. It's amazing, but what we also can't forget is that there is going to be a massive impact to data storage. If it's the HBM DRAM, if it's the local SSDs using TLC, if it's the network SSDs using QLC, or if it's the rotating media that is used for storage at scale. We are continuing to appreciate that we really can't predict the blue line, like where we're going to end up on potential TAM is kind of an unknown. And so we are excited to be a part of that equation. As I say, HDs are a part of the solar system. We're not, you'll see every presentation is SSDs, 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 but in reality, when you think about terabytes and petabytes and exabytes, the scale and the demand for data storage, HDDs are really still the main course for warm to cold data. So we are still part of it. Now our scales are at exabytes and megabytes, and that's not really what is used at the compute layer. So, you have to bifurcate compute storage, compute needs with mass data storage. So one of the enablers for that in our ecosystem that we've been exploring is how dual actuator enables us to match some of the demands for bandwidth that you've been seeing all week long. Dual actuator allows the file system to land data on two mechanical subsystems inside of one drive. If you go to our booth, you can actually see the two actuators in use. So it's a one-time shift, but it's a necessary shift if we want to align to the demands of the AI infrastructure. The analogy I use is a bucket of water. If you think of a bucket being the network SSD layer, you're putting a lot more water into that bucket, and either the bucket's going to overflow or you get a bigger bucket. But a bigger bucket is very expensive. So in order to prevent it from overflowing, you can drain it faster. And draining it faster is dual actuator. That's the enabler to not grow that SSD network layer to a larger size, which may be a way that you solve it, but it also is, can you actually get supply to solve that layer? Interface consolidation is, again, another way to enable performance like dual actuator, and also to enable bus efficiency and new commands in this topology, which this is a ratified spec through OCP. We were one of the big proponents of it. Working with our other peers, we're trying to appreciate how this type of architectural solution can help simplify the topologies that are being designed out there. And there's a lot of different solutions, with SATA, with SAS, and other protocols, but this seems to be one that aligns the network solutions on the SSD and the HDD together. But I also wanted to, talk to you about, we have a DGX, infrastructure as well at Seagate. We use it as part of work that we do with fluid dynamics for our mechanical platforms. We're looking at thermal aspects. So we've used some of these same tools as part of our design process. to help speed up, in this case, a 50 times improvement in simulation runs, right? And that what it's saying is that AI, not only are we part of the ecosystem, we're part of the we're a user as well, and so we've partnered with NVIDIA and ANSYS in doing some of that work, and and we use actually other technologies inside of the drive that help a lot with prediction of different things. That we've seen telemetry and other things as part of the AI conversation. A lot of our customers are using this data that we produce as part of their health checks of the system. So the world of AI and telemetry data collection is pretty important to understanding your fleet as well. One of the things that when you get to these scales of drives, when you're talking about a 30 terabyte, a 40 terabyte, a 50 terabyte, 60 terabyte drive, is that we've seen that about 40% of the failures are a single head. And so you're thinking about throwing away a drive that is really 95% healthy. And so your architecture has to be able to sustain coming back at a lower capacity, but this type of opportunity not to send an operator down to replace a drive is feasible. So you could have a 20 terabyte drive, simple math, a 20 terabyte drive, and one head goes bad, you would be able to come back as 19, right, and run healthy. Now, there are features that we're understanding that would potentially keep requires like a reformat and you come back as a new 19 terabyte drive, but there's regeneration where you come back as a 19 terabyte drive and all your data is still there. There's a lot of aspects around file systems that you need to manage differently to do that. But those are things where we're trying to keep the impact of failures to a minimum so that people can keep their environments up and running. So these are just different technologies, and what I'm trying to appreciate to the audience is that we're driven by capacity, but we have to innovate in other areas as well. And one of the things that we get pressure on is we're rotating media. We have we're limited by how fast we move and the rotation speed of the disk. So latency management is critical. Even though we're down the food chain, you still want things to come back in a timely manner. And what we've, in conversations with a lot of customers, is they want more control and more granularity to those commands that are in the ecosystem. And using command duration limits, they can put kind of like a bound on the commands that are in the system and say, hey, if you haven't finished your task by this amount of time, maybe we can get that other piece of erasure coded data from a different drive or different device, just kind of give up. And so these help with controlling your tail latencies and your number of nines of efficiency. So we're architecting this into our hardware, into our software, and working with customers to enable this. Again, these bigger solutions require a lot of customer support and standard support to make them a reality. So, basic disk drive understanding, you have a write and a read head, and you have a bunch of air flowing, and that head is flying over the media and magnetizing the media. The analogy is of an Airbus flying at 1,000 miles per hour, and for our fans of SI, 1,600 kilometers per hour, at about 1.5 feet above the ground. And that is what a head is doing over the media. That perspective this is something that was shown to me 27 years ago. I remember at one of my first, what are disk drive basics, right? And you're just like, holy cow, it's a 747 flying over the ground, and that has perpetually just come lower and lower and lower. It is still an amazing mechanical subsystem. And what is, when you think about areal density, you hear that term. When we talk about, that's basically tracks per inch versus bits per inch. You know, so if you think of something that's 1 terabit per square inch, it's roughly 57 nanometers by 11 nanometers, 10 to the minus 9. That is the granularity that you're working with at the media grain level. And what you're seeing in some of our new technologies is the stability of the grains get harder and harder. When you start getting to that level, the holding the magnetic charge at the grain level is very difficult, which is why we introduced our new technology with heat-assisted magnetic recording. So what is the servo subsystem? Another amazing piece of the equation. What does that mean? So if you think of a head flying at 1 nanometer with track precision of 3 nanometers, it's like driving a car at 80 miles per hour and you're allowed to drift off of center by no more than 5 water molecules. Okay, that is the level that our servo subsystem has to be precise. And you're talking about tracks that are 2,000 times thinner than the human hair. So what does that mean in all of the stuff that you've seen out there? What does that really mean? Well, you've got data centers running hotter. You've got cooling for all of this, the thermal aspects that are going on. Fans vibrate. You know, the drives are in that subsystem and they have to track, follow. And you're now kind of giving it a little bit of a shove. And we're able to stay on track, write your ones and zeros in an environment that's vibrating. That's what we do. That's what our servo engineers, mechanical engineers are continuing to innovate, because we're pushing tracks per inch even denser, right? That's how, when you get to the 40 terabyte and a 50 terabyte drive, we're enabling higher track density with this new technology, right? And it's an amazing, amazing subsystem. So HAMR's progression, you know, we're at the 3.2 terabyte. You can go and see it at our booth. You can see a HAMR drive in action, reading and writing. The movement to 4 terabyte, the movement to 5 terabyte. And you can say, well, is that really being demanded by the world? And we all have phones, we all take photos, we all create content. It is just still exploding. And as the age of the world changes, there's a lot of younger people and a lot of big countries coming online, creating more content. And nobody deletes anything, right? Which is a good thing for data storage in general. But that is the reality of the world, is nobody really goes back and looks at anything. Now, can an AI be used as part of that to go clean up data that's out there that hasn't been touched and 10 copies of the same thing? Sure. But we also know that inference and applications are going to create a bunch of content. Could you imagine writing a movie script, running it through AI, and you have a 2-hour movie that's created? You know, that is a very feasible thing. Instead of spending $200 or $300 million to make a James Bond movie, you just run it on your GPU cluster for, 2 or 3 months. Maybe it costs you 40 or 50 million, but it's still cheaper. And so those are things that require a lot of data storage, right, to that scale. So what is HAMR? So HAMR is new media, new heads. It's been 20 years in research and development. It is enabling the process of heating the media. So the heads are the same more or less technology, but now you're putting this heater that's in the lead to warm the media for nanoseconds before the actual writer comes on board. So if you think about that, you're on a cooling and a heating kind of immediate phase. So what we've actually demonstrated in Drive now is 4 terabytes per disk. And so we are, you'll see that platform coming out in the next X number of years, and 5 terabyte right behind it, and 6 terabyte. So we are enabling all of our customers to be able to, by the end of the decade, have data storage that matches potentially where AI is going. And it's honestly, very exciting to bring these types of technologies to reality at scale. You know, we're not making 10 of these per year, right? We're making millions of disk drives per year. And so to make them at volume, right? When I said there's 10 disks, that means there's 20 heads stacked together, right? And so if you think about manufacturing a head stack that has 20 heads and yielding it at volume, it's an amazing process, right? And we use a lot of, we capture a lot of that data. We do things where we take pictures of the drives as they're being manufactured, and we actually figure out defects in manufacturing from images before. So we're taking the person out of the cycle, and we use images. We do processing on them to decide where there's defects. Thanks. So where is this on this curve? You know, some of the colors, you know, what you're seeing is the designs of HAMR over the generations and how long we've been working on it. Because we knew the existing recording technology was plateauing. And you could say that a 20x terabyte drive was the end of that technology without the bump of HAMR. So with HAMR, we've done drive demos of 4 terabyte. We've done lab demonstrations now of 6 terabyte per disk, right? So you're talking about a 60 terabyte drive being demonstrated. Usually we're about 5 years from demonstration to product. That's a good analogy or time frame. So that's our goal, is to be able to get to a 10 terabyte disk, right? You know, we meet every 6 months internally, and all of the technologists get together and come up with a bunch of patents and create. And the goal of this time coming up is, what are the underpinning technologies to enable 10 terabyte? Now that's a TPI push, that's a BPI push, and so you know we're trying to enable more data movement without impacting power, because the power budgets seem to be going to our, like I said, in the solar system, the sun is getting all the power, right? So, and we're getting kind of shoved down in that. And as you've seen, a lot of their performance is achieved by parallelism. They're not getting the semiconductor improvements because the nodes are not transitioning as quickly. So it's not like, oh, I'll have a new chip that's half the power and twice the performance coming out in 2 years. They're just going to achieve that by having 2 chips, right? And that's what you see here in all these conferences. That's why they're trying to account for all that power. And so we have to also be part of that ecosystem, but we might not have the same budget. So here's this capacity, and you don't have as much power to play with. So we're trying to achieve a performance target, areal density target, potentially in less of a power footprint. So what's the call to action from us, right? Realize the role and significance of storage and our storage, HDD, in the AI workloads and infrastructure. Those checkpoints, the archives, they're still being stored on large data lakes of, you're talking exabytes of data, are still best suited on hard drives. The economies of scale. So how do we continue to innovate performance on megabytes per second per terabyte while ensuring a good TCO, dollar per terabyte, right? So how do we improve our megabytes per second but not blow the budget? That's pretty much, and how do we feed into the ecosystem accordingly? And then exploring interface and deployment simplification using NVMe HDDs. That's something we're partnering with some customers, working with the standards, but part of it is aligning the whole community to a new interface. And I've been through interface changes, you know, SCSI to SAS, and there's a lot of lift there. But this is the right direction for us as an ecosystem to go. Thanks.